What's going on, class? Welcome back to another lecture of mechanics and materials, aka solids. I'm Dr. Nee, and we're gonna get straight into today's lecture. And it's pretty much going to consist of us doing example problems. And that being the case, is all going to center around this equation right here. You've seen it before, MC over I. Of course, C is when we're looking at the max. If we're not looking at the max, then this is just essentially any distance away from the neutral axis. Moment of inertia, the moment at the location that we're talking about. So let's just keep that in the back of my mind. But in order to get to this, to use this, sometimes we're going to have to plot our moment diagram. So to start things off, we're going to look right here. Got something for you. That's right. We got some printouts, and we're going to go with question number or problem number 670. 670 is what we're going to look at. And it says, the strut on the utility pole supports a cable having a weight of 600 pounds. So 600 pounds is what we have here in this weight. Determine the absolute maximum. All right, we know what that is. The absolute maximum bending is the stress in the strata A, B, and C assumed to be pinned. All right, so this is assumed to be pinned. So that means that there's only one reaction. Only one reaction we're worried about here, right? Well, the resultant one, if it's pinned, it will be an X and a Y, but we can just worry about this resultant reaction. And then here, we can assume that there's going to be a X and there's going to be a vertical Y. We'll draw it going down. Matter of fact, let me go draw the free body diagram for you here. Here, we'll say CX. It's going in that direction. CY. We'll draw that down. And then we'll show this member AB as force AB. Let's do that. Force AB. And according to how our dimensions look, 1.52, this is a 3, 4, 5 triangle. So 4 is horizontal, 3 is there, and then obviously that's the 5. Coming over here, they've already told us that this here is a 600-pound force going down. And then let's keep the eye on this as well, because that's going to give us our moment of inertia, because this is the cross section of the beam here. But we'll come back to that in a second. First things first, let's sum the forces in the X direction. All right, we sum the forces in the X direction. We know all we have here is a, let's say, negative CX. Then we have a 4 over 5 times FAB plus, so 4 over 5 FAB. And that should be equal to 0. We can do the another equation, sum the moments about C, because we need to solve for either CX or FB before we can find out what we're looking for there. So let's sum the moments about C. And to sum the moments about C, well, we got these two forces here that's going to cause a moment. So if this is the positive, all right, we can say a positive moment is going to be caused by 3 over 5 FAB, right? The vertical component times the distance, right? What distance? Well, it shows us that it's 2 feet. So let's say 2 here. And then we have a negative moment that's going to create the 600 pounds. So we'll say negative 600 force times distance. The entire distance is 4. Any other moments? I don't think so. So we can solve for FAB in this case. And I'll let you do your own algebra by yourself. Pause it if you need to. But FAB in this case is equal to 2,000 pounds. 2,000 pounds. Do you concur with the professor? I hope you do. All right. So if you plug 2,000 pounds, right, 2,000 pounds up here, then we should get for CX 1,600 pounds. All right. So check that for yourself. We got CX. We got the value of FAB. Now we just need to know the value of F or CY, right? And to do that, what do? And if you said sum the forces in the Y direction, then you are correct. That is exactly what we do. We sum the forces in the Y direction. We have a negative CY, negative 600, negative 3/5 times 2000 equals 0. I'm sorry, that shouldn't be negative. That should be positive because this is going up. And the value of that should be CY is equal to 600 pounds. Do you concur? So we got 600 pounds, FAB there, and CX right there. All right, so what does the problem ask us to do? We are able to get all of our reactions, but it wants us to know the absolute maximum bending stress, absolute maximum bending stress. So the first thing we need to do is to draw our shear diagram. And I want you all to notice what we're doing in these particular examples. We're drawing our shear diagrams and our moment diagrams to help us know where we're going to take the maximum moment to get the absolute maximum bending stress. So the shear diagram starts off with CY going down 600 pounds. And then right here at FAB, the vertical component of it is going to be 3/5, 3/5 of 2000. Means that it's going to go up 1200. So it's going to go from a negative 600 to a positive 600. All right. And then obviously this force at the end is going to bring it down to 0. So what does that mean? What does that mean for our moment diagram? Well, our moment diagram should be straightforward and easy to draw. It's going to start off going down negative. So 600 times 2 means 1200. So it's going to go down linearly. And then up here, it's going to come back up linearly. And this value here is 600 times 2, which is a negative 1200. Let me make sure that's in frame for you. Boom. Negative 1200 is what your moment diagram will give you right there. All right. Now, so we need to know our maximum bending stress. Maximum bending stress, here's the equation. I told you at the beginning. I gave you a spoiler alert. It all comes around this right here. What is going to be the maximum moment? Well, we have it right here on our diagram. So we got that. Boom. What is C? The maximum distance from the centroid. We already saw up here. I told you to come back to that. So our cross section is like this. It's symmetrical. So the neutral axis, the neutral distance from neutral axis is 2 inches. Regardless of we're going to the top or the bottom, right? We're looking at absolute maximum, so it doesn't really matter. We know that's 2. And then we need this. Moment of inertia, it's a rectangular, so it's basically BH cubed over 12. Base is 2. Height is 4. And then 12 at the bottom. What is the value of that? What is the value of that? 2 times 4 cubed over 12. 10.667 inches to the 4th. So let's go ahead and solve this out. And that should give us our answer. The absolute max is equal to 12. Now it doesn't matter again. We're talking about absolute max. So I can just put 1200. That sign isn't going to matter because we're talking about absolute max. 2 over 10.667. Run that in your calculator real quick as I run it in mine. Times 2. And the answer we should get when it's all said and done. Look like we're missing something. Oh, okay, yeah, I know what we're missing. This here is in KSI. I mean, this here is in, this is pounds per foot. This is pounds foot. Right? This is pounds. So this is pounds foot. That means we need to convert it to inches. So this should have a 12 here. All right, that's what I forgot. So 1200 times 12 times 2 over 10.667. Let's try that now. 1200 times 12 times 2 divided by 10, 667. Boom. The stress here I have is 2699.9 psi. Or in other words, we could just say 2.7 KSI. 2.7 KSI, much more common, much more accurate. That is our answer for this problem. That is the absolute maximum bending stress in the strut. What do? We found our reactions, and I'm not probably gonna jump this part, move forward, because this is all statics. You all definitely should be able to do these equilibrium equations and get your reactions. But we got those. We were able to draw our shear moment diagrams. We identified where the maximum moment was, because again, we want to know the absolute maximum of bending stress. So that value here, 1200, is what we use for our equation. Of course, we had to find the centroid and the I in order to run that through. Don't forget to convert it to inches to keep your units consistent. And from there, you're good to go. You're good to go. Cool. All right, let's keep it moving. Let's move on to another example problem. And for this one, no, we won't do that one. We'll do 6-100. 6-100. All right. We'll keep it moving. 6-100. It says if D is equal to 450. Now, where's D? Oh, here's D right here. It's the depth of this beam, 450. We can go ahead and write it right here, millimeters. If D is equal to 450, determine the absolute maximum bending stress in the overhand beam. So we're going to continue we're going to do the exact same process, right? We need to know our reactions. We need to be able to plot it, the shear moment diagram, find where the maximum moment is taking place, use that maximum moment into our flexural formula, use that to find the absolute maximum bending stress. All right. So start things off. I'm just going to go ahead and give this to you because this is statics. And by now you should know how to do it yourself. So AY gives us a value of 10 kilonewtons. If you do all your equilibrium equations, you should get 10 kilonewtons for AY. And what you should get for AB, oh, no, sorry, AB, for BY is 34 kilonewtons. All right. If you want to make sure you can solve that correctly yourself, I encourage you to go ahead and pause it, go through the equilibrium equations, some of the moments where you need to, and solve for it as you should, right? But again, that's static, so we're going to keep things moving right now. So what we need to do next, one of the things we can go ahead and knock out is we can go ahead and find the moment of inertia, because we know that ultimately we're going to be using this equation right here, right? We're going to find this right here from doing our shear moment diagrams. We're going to know that. We can know that just from looking at this, seeing it is symmetric, right? So what would C be? Well, the height is 450, right? So C, the distance from the neutral axis, is just half of that, 225 millimeters, right? We'll come back to M. And then what is I? I think I can go ahead and calculate that, right? So I is base times height, but we have a big area in the middle of it. So one of the things that we can just do is simply take the moment of inertia of the entire cross section as if it's solid, and then subtract from it the moment of inertia of this space within it. So we'll do this. We'll say I is equal to base, which is the base of it, and we'll keep this in meters, or we'll not keep it in meters. We'll convert it to meters because that's pretty much a standard unit for this, for these. So the base, 25, 125, 25, that is that's 150, 175. All right, so 0.175 times height. Height of it is 450, so we'll say 0.45 cubed over 12 minus, what will the inner part be? Well, the base of this place space in the middle would be 0.125 times the height, right? So 75, that's 150, 150 subtracted from 450, that's going to be 0.3 cubed. So 12, all right? So I, right off the bat, we can calculate Excuse me. You all run it with me so we can make sure we are together. Nobody's fat finger in the calculator. 12 minus boom 1.25 3 cubed over 12. Okay, cool. So we'll write this as 1.0477 times 10 to the negative 3. That's meters to the fourth. That's our I. That's our I there. All right, so what we need to do here, we already got that, is go ahead and do our shear moment diagram so we can determine where our maximum moment is. So shear, let's start off with shear. And this is one of the ways that I was taught how to do it that helps, right? When you draw it right underneath, your image, right? You can kind of know that things are going to change at these points, at the support points, right? So to start things off, AY is going to put us up at a 10, positive 10 kilonewtons. And then we know that this is pointing downward, distributed load. So it's going to come down, right? It's going to come down. But how much is it going to come down? 4 times 8. 4 times 8 is 32. So we go from a positive 10 to a negative 22, right? And then it tells us that because we know that our reaction at B is 34, it's going to go back up to a positive 12 here, right? Again, right in line with that. Then nothing's taking place, so it stays constant here, and then there we have it. Our 12 is gonna, I made it a little longer, so I'll go ahead and come back down here. Boom, our 12 is gonna bring it there. So this is 12 kilonewtons. This is a negative 22 kilonewtons. Now, one of the things that we know, if you recall from statics, is that a point where the shear is 0, that's where you're gonna have a maximum moment. So we're gonna have a maximum moment. So we're going to keep that in mind for when we do our moment diagram down here. But in order to calculate that, we're going to need to know how far this is, like where exactly does this occur? And so to do that, we'll do similar triangles. We'll call this side X, and we'll call this side, let's see, 4 meters. So this is 4 minus whatever this X is. All right. So to solve for X, we're going to do similar triangles. We're going to place 10 over X and 4 minus X. I'm sorry, 10 over X and 22 over 4 minus X. So we'll write it like this. 10 over X is equal to 22 over 4 minus X. And then we go from there. We say 10 times 4 minus X is equal to 22X, right? We just multiply X to that side and we multiply that side, right? And then we go from there. We go ahead and distribute that 10 through 40 minus 10X. And we can bring that 22X back on the other side. Oh, no, not yet. I'll do this. I'll leave it on that side. And then we'll move the 10X to the other side. And we'll rewrite this as 40 is equal to 32X. Then we solve for X. X is equal to 40 divided by 32. What is that? 40 divided by 32 is 1.25. So X is equal to 1.25. So that means that this value, this distance here to here is I put in parentheses, 1.25 feet. So that's the unit we were in. 1.25 feet. I hope you all knew that, and I did it. That's something that's also covered in statics, but I'm not going to pretend like, everybody gets to this class and knows or always caught that. So thought I would show that to you one more time. So that means that we're going to start off here at 0 when we're doing our moment diagram. And because this is positive, we're going to know that we're going to go up to a point here. What value is that? What value is that? Well, that value is 10, 1/2 times 10 times 1.25. So 1/2 is the area of that triangle. So 1/2 times 10 times 1.25. 6.25. So that's what that is. 6.25. And that's kilonewtons meter. And then it's going to come back down here. It's going to come back down a different value, right? So it's going to go from 6.25 and it's going to come down 1/2 times. So this value right here, let's see, 4 minus 1.25. What value is that, right? Let's see, 4 minus 1.25. This is 2.25. 2.75, I'm sorry, 2.75. Right, so 1/2 base 0.5 times 2.75 times height 22 is 30.25. So we're going to go from 6.25 down an amount of 30.25, which is going to bring us all the way down to 24, negative 24. That's where we're going to go down to. Negative 24. I'll show that, scoot that up to you. And then we have here this last bit, 2 feet times 12. 2 times 12 is 24. And because that is a rectangle, it's just going to decrease at 1 order greater, back to 0. So that's our moment diagram. I hope that makes sense to you all. Now comes to really the plug and chug part, the part that we know all too well. What is the maximum moment, the maximum internal moment that we see, the absolute maximum? Is it the 6.25 or is it the negative 24 kilonewtons meter? Well, the larger number, the larger magnitude is right here, the 24. So let's go ahead and plug it into our flexural formula in order to get our absolute maximum bending stress. So this sigma max is going to be equal to the moment 24, right? Newton meters. And because it's 24 kilonewtons, we'll convert that just to regular newtons. So kilonewtons to regular newtons, we'll multiply by 1,000. And then from there, we'll get C, which we already know C to be half of this 450. So 225 millimeters, but we're putting it in meters. So 0.225. Put that all over I, right? Moment of inertia. 1.0477 times 10 to the negative 3 is what we'll go with. And let's see if you all can concur with me as I pull out my calculator and you do yours. So 24 times 0.225 divided by 1.0477. Okay, here's what I have. I have a large number if we're talking about Newton meters. So that's 5154147. All right, that's PA. And so if we were to convert it to MPa, it would basically be 5.15 MPa. Y'all with me? That was pretty much straightforward right there, right? We took the absolute maximum moment there, plugged into our flexural formula. We made sure our units were consistent, and then we solved for it right here in order to get the answer to what the problem axis, and that is the absolute bending stress in the overhanging beam. Good, we good? Excuse me. So here's what we're going to do right now. We're going to do one more. This one has a little, another little curveball in it that maybe it is really necessary or helpful for you to make sure you follow along. And so for that one, we'll look at, let's see. I'm thinking I haven't printed out. Yes, I do. 6-88. How about that? We'll do that one. Let's do 6-88. And here's the curveball I was just referring to. Right here, you have a hinge. All right, a hinge. How does that play into this? And does that make things any different for us? That is the question. We're going to find that out in just a second. Here's what the problem statement says. Find the absolute maximum bending stress. So if there was a title, there was a title of today's lecture in these example problems, it would be find the absolute maximum bending stress. That's what we've been doing. That's what we're going to do right here. But check this out. It says each segment has a rectangular cross section with a base of 4 and a height of 12. Well, instead of showing it to us in the diagram, it basically says that the cross section looks like this. Rectangular, height of 12 inches, and a base of 4 inches. What does that tell us about the moment of inertia? Well, the moment of inertia is found by doing base times height. Base is a 4, height is a 12 cubed over 12. Let's do that, knock that out really quick, right? Why wait? 4 times 12 to the cube divided by 12. And I got 576 inches to the 4th. There we are. There we are. Absolute maximum bending stress is going to come down to what? This equation right here. Sigma max MC over I. Boom. So we got that. We knocked that out just now, right off the bat. We know that our distance for the neutral axis is going to be halfway through the height because it's symmetrical. So this is obviously going to be half of 12, which is 6 inches. And we're going to do our moment diagrams, our shear moment diagrams to find that moment from which we are to get our maximum, absolute maximum bending stress. But let's go ahead and write our reactions. Let's write our reactions. So this is a fixed end right here. This is a fixed end. And we know that fixed ends have moment resisting moments. So let's draw a resisting moment right here and call it MA. Ordinarily, fixed ends also would have a horizontal reaction, but there are no other horizontal forces involved in this. And so we can leave that out right now. But I'm going to draw our vertical force here, AY. Not AX, AY. And then CY, that's right. I was about to draw something right there at the hinge, and we'll show you how to handle that in just a second. And you would find these, or you would find the value of these by doing statics. Again, I'm just going to go ahead and give you these reactions. If you need to, make sure you pause the video so you can make sure you know how to determine it for yourself. So AY, if you did your equilibrium equations, AY is equal to 26 kips. CY is equal to 4 kips. Right? And then MA, you will find it based on some of the moments around A or whatever way you wanted to determine it. But the value you should get is 153 kip foot. There you have it. Those are your reactions. And those are what we're going to use to draw our shear moment diagrams. Now, here's how you would do it. Here's how you do it when we have this hinge involved. We know at this hinge, at hinges, the moment is always going to be equal 0. So let's just remember that when we get ready to do our moment diagram, the place that lines up with that hinge should be equal to 0. But here's what you look at, right? You look at the fact that you're basically going to divide your beam up into 2 parts. And what you're going to assume is that at the hinge on this one, and let's draw the other one right here, right? Imagine this, that's the left side and that's the right side. At the hinge, you're going to have a vertical force that's counteracted by another vertical force where the hinge is located. But you're going to analyze these separately, right? Let's do it that way and keep our eyes on that. So we know here there is a moment of 153 kip foot. Boom. We know that there is a vertical force here of 26 kips. And then here we see that there's a distributed load of 2 kips per foot across 9 feet. So 2 times 9 will give us a resultant that comes right here in the middle of this. We can go ahead and draw in the middle of this portion of 18 kips. Now, so the question is, how do we determine what type of vertical force is going to be right here? Well, now we can just look at some of the forces in the y direction for this portion. If we were to sum the forces in the y direction, right, up is positive as it always is, what would it be? Well, here we would have positive 26, we have a negative 18, and then we have, let's just call this hinge, I don't know, hy equals 0. Well, by inspection, you can probably already guess, in order to make that equal to 0, you're going to need to have another value. When combined with the negative 18, it's going to cancel out the 26. What would that be? Well, hy is equal to 8 kips. So that means that this vertical force here is 8 kips. And because this is an equilibrium, that automatically gives us a head start that when it comes to this second portion, that this is also 8 kips. 8 kips. But let me finish drawing the forces here. We know 3 feet over. This here is a 12 kip force. And then over here, we have a vertical force, Cy, of 4 kips. So that's what the hinge is. Just know that there's going to be a counteracting vertical force that takes place. Internally, we know that the value is 8 kips, 8 kips. So let's come over here and draw our shear diagram. All right. Again, one of the convenient ways was to always show how it kind of lines right up with the diagram above it. So I'm just doing these little small connection lines. Keep making it too long though. But anyway, that should give us an idea of what we're working with. Imagine that's not there. All right, here we go. Starting things off, 26 kips, 26 kips. So we're going up 26 kips. All right, this is going to go downward at 2 times 18. So that's going 2 times 9, which is 18. So it's going to come down 26 minus 18 to a value of, well, what do you know? 26 minus 18 is 8 kips. This is going to stay consistent over here, moving over. And then it's going to go down another 12 kips, so from 8 kips to negative 4. Going to stay at 4. And then this is how you know you're correct, because the reaction right there at the end, the Cy, is also 4 kips. All right, so there is our shear diagram. That's our shear diagram. Now from there, we're going to draw another diagram. We'll draw another diagram. Moment. But guess what? Guess what? We're not going to start the moment at 0 anymore, because we see that this is a fixed end. So that means that there's going to be a reaction at that end. Now, this is an applied reaction here of a positive, right? But we know that the internal moment is going to be counteracting that, which means that it's going to start at a negative. So we're going to come down here and it's going to be a negative 153 kip foot. Negative 153 kip foot. And we know that right here, again, at the hinge, it's supposed to be 0. It's supposed to be 0. So one of the things we can easily tell is that this here is going to move from this point to this point 0. And because it's already linear here, it's going to be at an increased order. And it's going to look something like this. All right, so even more of a slope than the linear. It's going to be concave down. And then when we get over here, it's no longer linear. It's just a constant there. So now we're going to look at something that's continued to go in a positive, because this is on the positive side. But it's going to be 8 times 3, which is 24. So it's going to go up. We know we're going to be here at just a simple linear slope. 8 times 3 is 24. So that's going to be to 24 kip foot. 24 kip foot. And then we're going to go from there. Negative 4 times 6, or 4 times 6, which is 24. Makes sense. So that's going to bring us down here. Boom. That is our moment diagram. Practice these. You can definitely get used to doing this, and it can start going or flowing for you. But again, you remember these clues. You know, when it's a hinge, you know that your moment is going to be 0 there. You know that the value that you're going up or down is going to be equal to the area under the slope, or under the shear curve. Right? All these connections are really helpful when it comes to drawing these things. But with that said, let's get right to the home stretch. Sigma max is going to be the maximum moment. Well, it is 153 kip foot. Because this is kip foot, we're going to change the feet to inches, multiply that times 12. Then we're also going to change we're just going to put the 6 here for our C, and put that all over what we already found out very early in the process, 576 inches to the 4th. That's going to put us in KSI. So if you grab your calculator, as I grab mine, we can find the answer together. 153 times 12 times 6 divided by 576 equals 19.125 KSI. Do you concur, my friends? I hope so, because that, for problem 6-88, is the absolute maximum bending stress. Same process. Hope you all got it by now. Let me scoot that up so you can see the entire moment diagram. I'm going to keep that right there on the screen, because that concludes this lecture. We just ran through a couple of example problems, all centered around finding the absolute maximum bending stress in our beam, in our strut, and whatever member we were analyzing. And I hope that helps you all. Again, take some time, make sure that you can always know your reactions and your moment of inertia, and then draw your shear moment diagram, right? This just combines all of the concepts so far that you know, and you'll be good moving forward. All right, catch you all next time. Peace.